Hi, in this presentation, we will discuss granular materials and a subset of grains called superellipse sector particles, or CESPs. Specifically, we will discuss packings of these particles, which are collections of many particles interacting with each other and giving rise to some bulk material behavior. The reason we care about granular materials at all is because of their effect on our everyday lives. Granular materials can exhibit behaviors both like that of solids and fluids, which means they do not fit nicely into the traditional states of matter, being solid, fluid, or gas. This also gives rise to some really interesting complex physical behavior, specifically at the boundary between flowing and jamming. This is why things like grain silo failures, as seen in the middle photo, occur, and why hoppers that feed out those grains get clogged, amongst many other things. The material transitions from random loose packing to a more dense random close packing is not well understood and can lead to some expensive problems. In order to study these problems, physicists have tried defining a different simplified models of grains. Many of these models are only helpful in select cases, and so it becomes important to try to find a class of particle that can cover a wide range of particle geometries and single out the effects of different particle parameters have on packing behavior. On the left, we see one such attempt. This study uses the value eta to define a particle's divergence from spherical, a sphere being the most simple grain, in terms of non-convexity. This, however, does not at all define how the particle's aspect ratio or ability to entangle affect packings. The next study, the ones in the middle, take a step forward by defining aspect ratios and their relationship to particle entanglement and create rigid packings using long thin rods and staples. These experiments, however, do not propose a way to simultaneously study the effects of opening angle and also not the thickness of particles. The experiment on the right studies annular sector particles, or ASPs, which are a subset of CESPs, and they're made of a circle, some arc of a circle, and some defined thickness. This family of particles can only really study the effects of opening angles and thickness that they have on packing behavior. My work with CESP provides an important bridge between these simplified models of grains and thinking about more complex geometries found in everyday granular materials. Warning on the next slide, there's going to be some nasty looking equations, but I'll describe why they're important and how they work shortly. CESP are a great class of particle because studying them, you're able to smoothly transition different particle parameters just by changing the equation used to define a particle. Looking at the equation on the left, we see the superellipse equation written out in Cartesian coordinates. And on the right, we see its parameterized version. The exponents m and m describe the degree of curvature with respect to the x or y axis and are used to change the angularity of any given particle. The image of an asp and the image of a staple shown below are essentially the same equation, but the only difference being one has the staple has higher values of m and m. We also use the ratio of a and b to define aspect ratio of any particle. We can define the opening angle by choosing the range of theta to plot over for the Cartesian range, for the Cartesian equation, and the range of t to plot over for the parameterized version. We can smoothly transition between different thicknesses of the particles by defining a particle to be the set of all points made up some distance r from a plotted CESP equation, and the thickness of the CESP becomes then 2r. As you can see, the family of particles is able to address many of the shortcomings from prior experiments in terms of variability in particle design. In this way, we can do physics that is less stamp collecting information about highly specialized scenarios and rather takes a step forward in properly defining the world around us. One of the things we study using CESPs is excluded area. Excluded area is the area excluded from the center of mass of one particle as it nears another. This becomes important when thinking about free energy of packing of anisotropic particles, anisotropic meaning asymmetrical. Work by Lars Onsager using long cylinders was able to show that when particles pack in parallel, they give up some of their orientational degrees of freedom, but gain positional degrees of freedom. And this work is what made it possible for us now to use excluded area as essentially a replacement for entropy when thinking about granular materials. The study on CESPs, the study on ASPs, the subgroup of CESPs mentioned before, did a great job of showing how dimerizing is energetically preferred to the monomer state when under greater pressure. As can be seen, the stuff on the bottom of the packing is more dense and is mostly dimerized, whereas the stuff up on top is under lower pressure from gravity and is more in the monomer state. The work on the right is by my collaborator at RIT and has been studying excluded area of CESPs using a Monte Carlo method, where they basically try and place a CESP at random in some given region. If they can place the CESP down without overlapping with another, it's considered a success. If not, it's a failure, and and another random position is placed until it takes a really, really long time for any success to actually happen. Once the wait time becomes essentially asymptotic, you then stop the simulation and you say that you've reached something called random loose packing, which mostly just has to do with the geometry of CESPs and the geometry of the packings themselves, but doesn't tell you a whole lot about the mechanics of the situation, which is where my work with CESPs comes into play. I'll be using a molecular dynamics simulation to simulate the packings of particles and be able to study how they respond mechanically and show the transition from random loose packing to a more dense random close packing. The software package I will be using starts by having some initial velocity and position for every particle in the simulation. It then calculates any sort of contact force or long-range potential on those particles and takes some time step forward, where it then moves the particles, and it will calculate now, and then at the next time step, again, the forces of any kind, and move the particles again through another time step. Each time step there's assumed to be constant forces, and it just kind of does this over and over again until you've been able to simulate some sort of physical event. There are a couple problems with these types of simulations, or specifically the software. They're great for force calculations, but they're not great with making complex particle geometries. And so what I have to do is I have to create sets of points using Python, and then import those points into lengths. There's also a problem where rounding errors through the time steps can actually end up adding energy to the system and create non-physical solutions. And there's other problems where you think about how many particles can actually be simulated. A packing with 100 particles, each particle is going to have can have 99 different interactions with all the particles around it, and that's assuming there's no cross terms. And as you try to scale that up, it just becomes harder and harder and takes more and more computational power. With the resources at Haverford, we can do around 10 to the 4 particles pretty easily. 10 to the 5, you start having longer wait times. And this is kind of unfortunate because in any given cup of sand, there's usually around 10 to the 6 particles within that. And so these are some of the problems I have to work around when making my simulation. My procedure starts with taking the Python script and the points therein and importing them into lamps. I then place finite sized spheres over each point, which are going to overlap and essentially create a solid body. I then have to tell lamps that I don't want these spheres to exclude each other. I don't want them to like basically explode or create an explosion. I create one rigid body with all of these, and then what I do is I tell lamps to create a whole bunch of these particles and place them at random within some region. At this point, it's like pretty similar to the work that my RIT collaborator is doing. But then what I'm doing is I'm growing the particles. So I will increase the radius of the spheres. I'll also increase the length of the bonds between spheres in order to not just create a fattened CESP, but one that's actually just scaling up. As these CESPs come into contact with each other, there's dampening that occurs and there's a relaxation time before the next growth, so that basically every time there's a growth, the particles are stationary. And I do this until the net force in the system starts increasing exponentially, and that tells me that particles are no longer able to rearrange and find a more dense packing. And so I'll stop there, and that's when I know I've reached random close packing. And that's when I'm studying a lot of the mechanics on the way to random close packing and what happens at random close packing. I'm also going to be studying this in parallel with a rotating drum experiment in the lab. This is similar to what Colby will be using for his experiments. So for me, I'm going to be putting in laser cut CESPs, and I'm going to be tracking those using a high-speed camera. And I'm going to be studying the both mechanics of these particle packings as well as polymer population statistics and how that affects the dynamics of any particular packing. In summary, research in the field of granular physics has long strived to find a way to generalize particle types and single out the role geometry plays in the behavior of packings. CESPs offer a family of particles which can be finely tuned for particle parameters in order to single out their effects on material behavior. We believe that studying using both molecular dynamics simulations and in-lab experimentation will give a wide range of data to analyze and advance the field of granular physics. I can now take any questions. Thank you.